Hello everyone, I'm Sreeshma Shiv. I'm a PhD student from ECE Department IAC. I work with Professor Rajesh Sundareshan and Professor Anurag Kumar. I'm presenting our work on rate guaranteed fare scheduling, for which I was also getting guidance from Professor Chandramurthy. We are working on finite time analysis of gradient scheduling with a slow timescale index bias for accurate GBR slicing in 5G cellular networks. One of the requirements of network slicing in 5G networks is RAN scheduling with guaranteed bit rates for a subset of the enhanced mobile broadband UEs. That means network slicing augments the EMBB services by enabling the operator to offer minimum rate guarantee to some of the UEs. Assuming that the rate guarantees are feasible, this yields a problem of utility optimal scheduling with minimum rate constraints. Now, what does that mean? A classical scheduler, if you take without any rate guarantee, standard formulation for obtaining the downlink throughput to each UE is to maximize a non-decreasing concave utility function over all possible throughput vectors that can be provided by any ergodic scheduling policy. These throughput vectors that can be provided by any ergodic scheduling policy are called rate region. In summary, we maximize the utility function over the rate region. And from literature, we know that gradient scheduling algorithm asymptotically yields the utility optimum throughputs for this problem. And now coming to our problem, it's the same utility maximization with minimum rate constraints for some of the UEs. To tackle this problem, we have an algorithm which we call as PFRG-LM. This is a 2-time scale algorithm which uses gradient scheduling with a bias. That is, the algorithm introduces a bias which we call as index bias to the gradient scheduling indices for users with guaranteed rates. And these index biases are updated over time using a stochastic approximation method. This uses a slower timescale compared to the EWMA rate update that is done based on gradient scheduling indices. What I am working on is finite time analysis of this algorithm. We derive finite time bounds on the expected L2 norm error for each iteration from their optimal values, and we also get some insights into the choices of time scales of each iteration and how they play a role in these error bounds. With this idea of what we are doing, how is it done, and why is it required in a higher level, now I'll go to the mathematical formulation of the problem. Problem model is we have one base station and it has to schedule MUEs in each slot, and out of these MUEs, M1 UEs has rate guarantee. So the optimization problem will be maximize some utility function subject to the constraints R belongs to R bar and Ri greater than or equal to Ri min for the M1 UEs. So U of R is some utility function which is chosen to be strictly concave, G-smooth, coordinate-wise non-decreasing over R bar and continuously differentiable. And the average rate region R bar is convex. Now, given that a strict concavity of U and a convexity of rate region R bar, we get a unique vector of optimum rate theta star belongs to R bar. Now, the scheduling problem will be in a slot given the states S of k and the EWMA throughputs theta of k, determine a rate assignment R of k in each slot so that the vector of EWMA rate eventually gets close to this theta star. Now we consider the relaxed version of the problem, maximize U of R plus summation I equal to 1 to M1 UI Ri subject to R belongs to R bar. So we define this as our modified utility function phi of R, and since this is strictly concave objective function to be optimized over convex set, again we will have a unique solution, and we denote this unique solution for fixed nu to be R of nu equal to x of nu y of nu, where x of nu is the rate for M1 UEs which has rate guarantee and y of nu is the rate for M minus M1 UEs. The original optimization problem can be solved by adjusting the multipliers nu until when solving the relaxed problem in equation 2 we get x of nu equal to R min. That is the idea from where the PFRG LM algorithm comes from. Now, the algorithm R star in each slot is calculated using gradient algorithm applied to the relaxed optimization problem with new S parameter. So it does argmax of gradient of phi dot R, where R belongs to the rate region for that particular slot. Then it updates the AWMA rate theta k plus 1 equal to theta k plus A R star minus theta k. So the AWMA rate here is updated with the time scale A. These two iterations together, we call it as primal iteration. Primal iteration solve the optimization problem in equation 2. That means if the two iterations cause the theta to track the solution R of nu. So especially if you consider the rate guaranteed uses, theta xk will track x of nu. Now, there are multipliers nu. This should be adjusted on a slower time scale to achieve equality x of nu equal to r min. So then we have the update equation nu k plus 1 equal to nu k plus b r min minus theta k plus 1 with a bound 0 to nu max. We call nu I index biases as they bias the usual phase scheduling indices to encourage more frequent scheduling of the UEs that require rate guarantees. Now, coming to the fast iteration analysis, consider this is the solution for the optimization problem in equation 2, and this is what we get as a sample path time average of iterates over T slots under PFRG LM algorithm. And D is the diameter of B, where B is a set of all transmission vectors available. Then we could prove the theorem if phi of R is G smooth and alpha strongly concave over R belongs to B. Then for all t greater than 0, the fast iteration of PFRG LM algorithm yields expectation of norm square of the difference between average rate and the optimal solution for the optimization problem is less than or equal to agd square divided by alpha plus 2 by alpha phi of r of nu tau minus phi of 0 divided by at. As you can see, the error bound depends on a and t. This gives insights into how to choose them for minimizing the error. Then coming to slow iteration analysis, we have two lemmas. First lemma discusses properties of rate region. So we are describing rate region as in terms of some g of xy less than or equal to 0, and we can say that g of xy is convex and twice continuously differentiable. The proof for this uses the concept of convex conjugate functions to write the expression for g of r in terms of another function and then applies the inverse function theorem. And another lemma says x of nu is continuously differentiable in a neighborhood of nu. The result is established by applying implicit function theorem to the KKT condition equations associated with the relaxed optimization problem. We are interested specifically in the properties of the rate components corresponding to the rate guaranteed uses as you can x. This is because our index bias iteration or slow timescale iteration analysis depends on the behavior of these variables only. So here the index bias update equation is given as nu x tau plus t equal to nu x tau plus a x min minus theta x with bound 0 to nu max. So here the subscript x means this is for rate guaranteed users, and for non-rate guaranteed users your nu will be 0. Recall that x of nu tau comes from the solution of the relaxed optimization problem for fixed nu tau and define nu star as the value corresponding to x min, which gives x min equal to x of nu star. And over the course of iteration, the multiplier vectors nu approaches nu star so that x of nu is equal to r min. We now establish the bounds that characterize this convergence behavior. So this theorem gives an error bound on del tau plus t, which is the difference between each iteration of nu and the nu star. So first part of this error diminishes with each iteration due to the factor lambda m, which is less than or equal to 1. As a result, the dominant contributor to the residual error from this is from primal iteration and lambda m and a. This proof requires some more work. It is yet to be finalized, even though we have a complete proof for case with 2 UEs and 1 UEs with read guarantee. General proof has 2 gaps, which we are still working on. So with that, yes, I'm concluding the talk. Thank you.